Alright, so in this video lesson, let's learn how we can work with direct variation. Alright, so the idea here is quite straightforward. So now allow me to indeed bring in the formal definition of what it means by direct variation. Alright, so on my computer screen right here, this is the definition, and this is the way how we understand about what direct variation means. So for any two variables, x and y, now when we say y varies directly with x, if y equals k times x, so we have an equation here where k is a non-zero value. And so we have a definition here that k is a constant value that's called a constant of variation. And so I want anyone viewing the video lesson here to pay attention a little more closely to this line right here. And as a matter of fact, let me now highlight that. So the line that specifically say y varies directly with x. So this is one the phrase with the proper verb and nouns and all that. So on the board here, allow me to make that translation from a verbal language, from a written language into a mathematical language right here. So it says y varies directly with x. So this is one statement, but when it says so, and y is a variable and x is another variable. So when we say y varies directly with x right here, so just y varies directly automatically brings up y equals, y varies, we write that in mathematical language right here, y equals, and then directly with x, that's what brings up y equals k times x. I purposely want to bring this up so that you can notice, because this phrase right here will appear very commonly among any kind of problem that you're doing, as long as you're working with direct variation. And so in that way, the way it will be stated out there will always be the same. You may be working with different variables, names, and all that, but in the end, anytime that you run into this phrase right here, a variable varies directly with another variable. So that variable that varies, you put that on one side by itself, on one side of the equation, and then make that equal to the other variable multiplied with a constant k, with a coefficient k, like that. And so that's everything we need to understand about the structure of this phrase and how we translate that into a mathematical equation. And so now let me bring up an actual example to show how we can use this understanding into problem solving. All right, and so in this example that I brought up on the screen right here, let's read the description here verbally a little bit. So when Raul runs on the treadmill at the gym, the number of calories that's named with the variable c right here, the number of calories c that he burns varies directly with the number of minutes m he uses the treadmill. So m is the number of minutes he uses the treadmill. He burns 350 calories when he used the treadmill for 18 minutes. How many calories would he burn if he ran on a treadmill for 25 minutes? All right, so allow me now to leave the problem being kept on one corner of the screen right there. But now let's look at the way how it's worded. So we already identified two variables. So in my style of working, in my way of working with direct variation, then first thing I'm doing, I'm going to be identifying the variables that we can find from the problem. So the wording is still here. What it says, mainly we have the number of calories. So C here, in the way how it was indicated, C represents the number of calories. All right, and so for the rest of the problem, I will not have to keep mentioning the number of calories and the number of calories. I can just refer all that here as the variable C. So C represents the number of calories that he's going to burn. And then according to the problem, how it's stated, I have another variable m that I can identify. This letter m, this variable m right here represents the minutes, the number of minutes. Okay. he uses the treadmill. All right, and so I may not write down precisely how it's written and how it's stated from the wording of the problem, but now we have clearly two variables. So now let's look at the wording one more time a little more closely here. So in the way how it's stated, the number of calories he burns varies directly with the number of minutes. Again, the number of calories, which is C right here, the number of calories he burns varies directly with the number of minutes he uses the treadmill. Let me now even highlight that. The number of calories that he burns varies directly with the number of minutes that he uses the treadmill. So in this way right here, on my board, the number of calories is C. C varies in another more closely related to a mathematical language. C varies directly with M. C varies directly with M. So another way of understanding it, C varies directly with M. And so this is now how I recognize the exact structure that we have seen in the definition of what it means by being being a direct variation. And so now in this way right here, I can immediately come up with the equation. So now that means, mathematically speaking, we have C as the variable equals to some K constants multiplied with M. So now our equation here, this statement that we stated in words translates into a mathematical equation. So now we have an equation C equals Km. And again, K is a non-zero constant, and then multiply with M being the other variables. So we have two variables here that we already named and identified here. And so now from the problem right here, let's look a little further into the wording of the problem to extract out some further information. So now he burned 315 calories. So this indicates that C equals 315 calories. He burned 315 calories when he used the treadmill for 18 minutes. So this statement right here on my board indicates that C equals 315 at the same time when M is given to be 18. And so now this M value and this C value, these two values for M and C, these are all given. A little bit back to the earlier step I was doing before I extract out this information. In this relationship, and in this video lesson, it may be a little early for someone viewing the lesson, but allow me to introduce that. So we have two variables, but now in this relationship right here, I refer to the variable C right here as the dependent variable. I call it that way simply because if we change, or anytime we change the value for M, the value for C will be changed, will come out differently. And that's why it varies. The value for C varies depending on M. And that's why I call C right here, I refer to C here, it's a variable, but I refer to C here as a dependent variable, which means the value for C depends on the value for M right here. And so now back to this line that I was having right here, I extracted out this information from the wording of the problem. And so now with that information that we have found, the equation we have, C equals K times M. And again, when C equals 315, M at the moment, M at that value equals 18, or in the other way of saying, when M equals 18, when he spent 18 minutes on the treadmill, C comes out equals 315 calories. So that means I am going to substitute the value 315 for C. So I'm looking at 315 equals the K. We didn't have a value found for K throughout the wording of the problem. I'm leaving it there. But M here can be substituted by 18. And so again, what I just did, I substitute 315 for our variable c. I substituted 18 for our variable m right here. And so now at this point, I have realized I have produced an equation, a very simple equation in a more friendly look right here, 18k, where k is our unknown, 18 times k to equal 315. From this equation that we have found, that we have arrived at, we can simply divide both sides and solve for k right here to find the value for this unknown k. And so in that way right here, k will be equal to, and of course we have learned enough math up to this point to know that the left hand side here, we can cancel the 18 away. That's why we arrive at k equals whichever value that comes out from 315 divided by 18 here. Calculation of mine show 315 divided by 18 would give me 17.5. So 17.5 now is the value for our variation constant. And so now, once we have found the value for k right here, we can actually indeed complete our equation. Recall again that our equation at the beginning was simply just, yes, we know it's a relationship c equals k times m, but we did not know, at that earlier point, we did not know the value for k. But now, after this point right here, we can revise our equation to make that become c equals, now 17.5 is going to be substituted properly for k. And now our equation is completed as c equals 17.5 m. So now we have a clear relationship that shows how the direct variation goes. So this is our equation that shows the direct variation for this particular problem. And so now back to the wording of the problem, the question is really asking how many calories would he burn if he ran on a treadmill for 25 minutes. So we want to find out how many calories. What value equal to c? In other words, what value equal to c when m equals 25? So now that we have come to a complete equation that describes our direct variation here, m is given to be, or is known to be 25. Then in that case, we are going to simply substitute m, the value for m, into this complete equation of ours right here. And so in that case, c, the number of calories that he burned, will equal 17.5, but now multiply with m substituted by the value 25. Now we have a final calculation, and once finished calculating this value right here, that is how much, that's indicating how much calories that the road burned. So in that case, direct calculation of mine shows 437.5 calories. And so this is the final answer right here. That answers the question. Once again, the question was asking how many calories would he burn if he ran on a treadmill for 25 minutes. And so now I'm stating that at 25 minutes on the treadmill, he burned 437.5 calories. And so now with these steps being written down on the board right here, from this board here to the other board, from the beginning to the end right here, let's look through the steps and recognize the general structure of how we solve that problem, because that problem I've just now done in the example was a very common problem. It's not just about how much calories being burned over the number of minutes on the treadmill. It's not only just that, but it's just basically any direct variation problem. That's the way how it's done. So let's recognize a general method of how we can do that as a how-to instruction. So on my screen here, I have come to the following how to solve a direct variation problem. The problem that we have just now done represents the following steps. Step 1, we identify the variables and write the formula for direct variation with the identified variables. So right here in step 1, this is what I did. The work I've done here, I have first identified the variables and named those. And then this was just something to help recognizing the equation. But once we have identified the variables, we come to that relationship, we come to that equation that represents our direct variation. So by this point right here, that's the end of our step 1. And now on step 2, we are going to substitute the given values for the variables. One more time back to this board. One more time back to this board right here. I have found throughout the wording of the problem right here the value for the variable c and the value for the variable m. So substituting the value for m and c into the equation is done by this step right here, where I have substituted 315 for the value as the value for c and 18 as the value for m. Then on our how-to instruction steps right here, third step, we solve for the constant variation. We solve for the constant of variation. Constant of variation right here refers to the value of k right here. So this k right here is our constant of variation. So the work I was doing here was in the purpose of solving for our value of the constant of variation. And so up to this point right here, I have completed step 3. And so once we have solved for the constant of variation, now step 4 here, we write the final equation that relates the variables. The final equation that relates the variable. So on my board here, this is the final equation that relates the variable. It's the final complete equation that relates c equals 17.5, some constant 17.5. We found that constant 17.5 multiplied with m, the other variable. Then ultimately, the last step right here, we use the final equation to find the value of the dependence variable. So earlier I was introducing that term right here. This variable c in our relationship here is called the variable that varies directly in terms of, or with the other variable, the variable that varies directly in our the problem. We refer to that as the dependence variable. And so the step just now, I have substituted the value given, for this variable m, and in that way I have calculated, or I have found the value for the dependent variable. So c was finally found to be 437.5 calories. All right, in this lesson, let's learn how we can solve a problem by using inverse variation. Now allow me to bring in on screen what it means by being an inverse variation. All right, so on our screen right here, this is the definition for what it means by being an inverse variation. So for any two variables x and y varies inversely with x if y equals a constant k divided by x, or more commonly speaking, y equals a k over x, where k here must be a non-zero constant. And the constant k here is called the constant of variation. And for anyone viewing this video lesson, I want you to pay attention more closely to this phrase right here. As a matter of fact, let me highlight that. All right, so what it says here is y varies inversely with x. So here's how I help myself recognize it. When it says y as a variable varies inversely with x. The way how I'm seeing it, this is a complete sentence. This is a complete statement right here. Y is the name of one variable. It varies inversely with another variable. So now to help you recognize the equation, the relationship, from now on when you see y varies, that will automatically translate into a mathematical equation y equal a mathematical statement, y equals. And then inversely is a property inversely with x. So this phrase inversely with x right here indicates that y varies as k over x. And so that's how I can help myself translating this verbal statement into a mathematical statement as an equation right here. Okay, and so this way of how it's worded is very commonly used out there. And so anytime you see one variable varies inversely with another variable, it automatically translates into an equation like this. And so now let's see how we can use this understanding into some actual problem that we solve by using inverse variation. All right, so now on my computer screen right here, allow me to bring up an example. So in this example, let's read it out loud right here. The frequency of a guitar string varies inversely with its length. A 26 inches long string has a frequency of 440 vibrations per second. How many vibrations per second will there be if the string's length is reduced to 20 inches by putting a finger on a fret? All right, so now allow me to leave the wording of the problem at the corner of my computer screen right here. All right, but let's now identify the variables being involved in our problem right here. So I see the problem mentions about guitar string length. So it's a quantity that can change. And so why don't we name this quantity here as a variable L? So the guitar string length is the variable L right here. And so in our problem, you can see that a guitar string's length can be anywhere from, you see, 20 something inches to 26 inches and all of that. So now it's completely legitimate that we name this, we name L here to be a guitar string length here. Now aside from that, I also recognize the number of vibrations per second. All of that is represented is referred to as the frequency. So here, frequency, okay, or another way of understanding it, the number of vibration. Okay, the number of vibrations per second. Right? So this is more like the measurement of frequency, but that's how we call it, the frequency. But now we can name, because you see, longer guitar string result in some frequency, and then shorter guitar string result in some different frequency. So frequency here can be understood as a variable. So how about let's name it F. So now just right now, according to the wording, I have identified two variables existing or being involved in our problem right here. All right, and so now let's read more closely into the wording description of our problem right here. So the frequency of a guitar string varies inversely with its length. The frequency of a guitar string varies inversely with its length. So right here in the very first statement that I highlighted in yellow, highlighted right here, I can immediately recognize the frequency varies, the frequency as F, frequency of the guitar string varies, again, I'm stating that in a more condensed form. The frequency varies inversely with the string length. That means inversely with L. So here's one variable. F varies inversely with L. F varies inversely with L. So I tend to put the actual wording into something that sounds more mathematical, and so that I can now easily translate this immediately into the equation, an equation that points out the inverse relationship. So F varies inversely with L. So now I'm gonna put K over L. So F varies inversely with L. Just like how I have mentioned y varies inversely with x, result in the equation y equals k over x. Now, similarly, f varies inversely with L, results in that equation f equals k over L. And so this equation right here points out the relationship between the two variables involved in our problem. Allow me to call this variable f right here the dependent variable. It may be early for some viewers now to learn the new term dependent variable, but in a simplest way of putting it, as the value for L change, as we change the value for L, the value for F here will change. L represents the guitar's length, the guitar's string length, and F here is for the frequency, how many vibrations per second right here. And so as we change once we change the length of the guitar string, then the frequency will also change. And so these two variables, they're all changing their value, but the value for F changes depending on the value for L that is given at the moment. And that is the reason why we refer to this variable here as the dependent variable. And now let's continue reading further into the wording description of our problem here to see if we can identify some further information. So, a 26 inches long string has a frequency of 440 vibrations per second. This information now to us is very beneficial. What it said there is that when L equals 26 inches, at that moment, or at that specific length of a guitar string right here, we come out with frequency to be 440. But now what it tells me here is that at this moment we are having two given values for our corresponding variables L and F. How it's useful for our problem is that once we know those two given values, L was given to be 26 and F was given to be 440. Back to our equation that we have stated earlier, F equals K over L. I can now substitute this pair of values. 26 will be substituted for L, 440 will be substituted for F. So this equation here will become, in my next step, 440 after I substituted the value into for F to equal K divided by 26, because I have just now substituted the value for L that was given here into our equation. So at this point, all of a sudden we realized we have produced for ourselves an equation 440 equals K over 26. This is an equation that's very simple to solve. We are about to solve for K to find out the value for our K right here. So to find the value for K, I am going to simply multiply that 26 to that other 440 value on the other side of our equation. So that means K equals 440 multiplied with 26. Or in a more friendly way of presenting the step right here, I'm writing K equals 440 and multiply with 26. Calculation of mine shows 11,440. So this is what I have found out for my constant of variation. And so at this point right here, back into this equation that was stated here earlier, we can now further complete that equation. We can further complete that equation as following. So F now is equal to 11,440 divided by L. So I have just now found my complete equation for the inverse variation between the frequency of a guitar string and its length. And now back to the wording of the Example, how many vibrations per second will there be if the string's length is reduced to 20 inches by putting a finger on a fret? But the most important information is here. We want to calculate the number of vibrations per second when the string's length is given at 20 inches. According to that worded instruction or description right there, at that moment we're given that now when L equals 20 inches, no longer 26. Now what happened when L equals 20 inches? We want to go from here to calculate the corresponding value for the frequency of the guitar string at that specific length. And so in this case right here, I am simply just gonna substitute this value into our complete final equation here. So what I have now is F according to this inverse variation. F equals 11,000 as a formula, 11,440 as a formula, divided by 20, where I have just now substituted 20 into our equation. Calculation of mine showed 572. So this is the value of the frequency corresponding to the guitar's string length to be 20 inches. And so what it says now is that at 20 inches for a guitar string length right here, that string with length 20 inches will vibrate 572 the vibrations per second. 572 vibrations per second. And so we have now found that final value right there. All right, so we can now generalize the steps we have done in the example just now into a how-to instruction. So here we come to the how to solve an inverse variation problem instruction here. So step 1, we identify the variables and write the formula for the inverse variation with the identified variables. So for this step, what I did there on the board here, I have identified those quantities being involved in our problem and named those variables. So I identify the frequency of a guitar string into the variable F. Naming is our choice. The guitar string length, I named that with the variable L. That's how I have identified and named the variables. And now right after that, I recognize that this statement right here is recognized throughout the wording of our problem. And from that statement, we now formally put that into the equation that relates F with L here by that inverse variation relationship. And now with step 2, we substitute the given values for the variables. So earlier when I was going through the problems, I identified these two given values from the worded description of our problem. So what it said here was that when L equals 26, we had the frequency of the guitar string to be 440 vibrations per second. And so in that case, the next step that I moved on this board right here, I substituted those given values into the equation. So again, I wrote down the equation here, and I substituted 440 for F and 26 for L. And that's what I did in step 2 right here. So right here is the end of step 2. And then moving on to step 3 right here, we would solve for the constants of variation. So that step in step 3 is where my work is being shown right here. So these little steps, or for step 3, where I'm solving for the value for K right here. So after substituting in 440 for F and 26 for L, I multiply 26 to the other side, and then that's how I calculated the value for K. And this is the value for our constants of variation. Then for step 4, we write the final equation that relates the variable. The final equation refers to this equation right here. So once we have come to the value that we have found for K, the constants of variation, then the final equation looks like this. So F is the dependent variable. That equals 11,440 divided by L. And then after writing the final equation that relates the variable, the last step here is to use the final equation to find the value of the dependent variable. And this is to mention That's the reason why I introduced that term being the dependence variable. So f here in our equation, in our inverse variation, is in this relation of our representing our inverse variation. Then the f here is referred to as the dependent variable. So now with the final equation, f being our dependence variable and L being our and L here is being part of the problem right here, then you see we now calculate, or we find out the value for the dependent variable by substituting in the given value, another given value of our variable L into the complete equation. So that's how I had 11,440 divided by 20, because this 20 was substituted for L. And so now that final calculation came out with 572 vibrations per second. And that's how I have found the value for the dependent variable based on the given value for the main variable.